All right, welcome everybody to this second day of our second annual SU2 conference. My name is Piero Colonna. I'm a professor at Delft University of Technology and a member of the board, and it's my pleasure today to chair this first session. The first talk today will be given by Dr. Pini and Dr. Anand of my same group, Propulsion and Power, at Delft University of Technology. Matteo, the floor is yours.
Thanks a lot, Piero. It's a real pleasure for me and for Nitish to be here today to talk about what we have been doing in the past 7 years and what we'll do in the next. So I'd like to provide an overview of the turbomachinery analysis and design capability of SU2 and looking back, but more importantly, looking forward. And before we start, we'd like also to acknowledge the contributions of Antonio and Salvo, who greatly contributed to the development of all the turbomachinery features that are now available within SU2. So let me start. Okay, let me start by recapping what we have been doing in the past 7 years and showing you a bit the history of SU2 for turbomachinery flow. So we initiated the development of turbomachinery features quite few years back in 2014. And the first feature that we implemented were two-dimensional non-reflective boundary conditions, because at that time we were interested in supersonic turbine applications. Then along the years we moved on, and after that we focused our efforts on the implementation of mixing plane, and we achieved full functionality, full 3D mixing plane functionality within SU2 around 2016. Then around 2018, so close to those years, we are able to perform 3D steady state optimization with FFD, even for multi-zone problems, and to perform the first unsteady computations of Stator-Rotor interaction in various kinds of turbomachinery configurations. Then more recently, we implemented reduced order models like harmonic balance for the efficient computation of steady turbomachinery flows and developing the related adjoint counterpart. And because of that, we went on and moved towards more multidisciplinary analysis and multidisciplinary optimization. And most recently, we have been able to do Aeroelastic analysis and design with SU2, coupled to our CAD-based parameterization software to enable Aeroelastic design optimization. And Nitish, in the following, will show you an applicative examples of what we have been doing in recent time. So as a recap for the community that is attending the talk today, what is available within SU2 as of now with respect to turbomachinery features? First of all, we have available a bunch of features: no reflective boundary condition, mixing plane, sliding meshes, harmonic balance for even pitches. Then we also inherited the most recent implementation of neutron Krylov solvers, and we have been able to improve the speed and robustness of the machinery flow computations with the neutron Krylov. We also work on implementing some ultra-fast methodologies for computing to machinery flows, relying on what is called body force modeling. And all of these features come along with the discrete adjoint counterpart. So nowadays, not only the analysis problems can be run with SU2, but also design problems. And the code is also equipped, there is a bit of lag, apologize, with also models for computing thermophysical fluid properties with equation of states other than for the perfect gas law. Now, the point is that, yes, we have a bunch of features, but not all of them are available in the develop for one reason or another. Some of them, like the harmonic balance, they're spread over few branches. And that is exactly the reason why a few months back, we started a project called that we baptized SU2-Evo, with the final intent of merging the most important machinery multi-zone features into the V7, into the latest version of SU2. And in parallel to that, we are also interested in adapting the multi-grid capability for enabling multi-zone periodic calculations. And this work, this effort has been pursued in collaboration with Imperial College and University of Cagliari in Italy. And here I'm showing you one of the first example of turbomachinery computation with multi-grid capability activated with mixing plane also. And as you can see, with multi-grid, with two-level W cycle, we're able to obtain convergence in 2/3 of the iteration needed to obtain convergence without multi-grid. And now, having said that, I would like to move on to the core of the talk. And Nitish is going to illustrate you about what we can do nowadays in terms of optimization with SU2 and a couple of applicative examples. And I will close this talk by explaining what, in our opinion, should come next and what will come next.
Thank you, Matteo. So, well, let's look at the design chain that is used for our application. So we have these 4 blocks, which is, let's say, surface deformation, volume deformation, grid movement, and flow solver, in which we go from alpha, which is like a set of design variables, to our objective function J. Now, the grid movement is necessary only if we want to do an unsteady simulation with the motion of the mesh, but it is not required if you are doing unsteady simulation in which we have some kind of inlet unsteadiness, or if it's a steady state problem. Now, over the years, we had a lot of problem with free-form deformation boxes for parameterizing the blade surface, and that is primarily because the parameterization, it was very difficult to put certain kind of constraint on the parameterization. Now, that's why we have developed the software ParaBlade in last couple of years, which contributes to this part of the equation. And the later part of the equation is coupled with ParaBlade so as to obtain the final sensitivity of the objective function with the design variable. Now, ParaBlade is a parameterization tool in which we have a camber line and thickness distribution based on which we can have a 2D definition of the blade. And this 2D definition is extruded at every span and are connected by a certain kind of variation in the properties in the span-wise direction, using which a full 3D definition of the blade can be get. Now, the ParaBlade might sound a bit smaller name and might define that it's just used for parameterization, and that's not true. There's another part of the code which does the optimization, which kind of does the job of orchestrating the entire optimization process, from parameterization to getting the sensitivities to running SU2 and then doing the matrix multiplication and providing this back to the optimizer. Now, this helped us to detach from the ad hoc shape optimization Python file within SU2. And now with this one, we can have, let's say, more flexibility with respect to the kind of algorithms that we can use, but also with respect to the kind of problems, for example, multi-point and multi-objective optimization problems. So based on that, I'm going to show you 2 examples. So one is an aerodynamic shape optimization and one with Aeroelastic. Now, for the aerodynamic, we have been interested in this multi-stage computation for a very long time. So in this study, the idea was to compare the mixing plane approach with the harmonic balance approach and see what kind of differences in the geometry we can get in the final design. Now, in this case, we have approximately 195 design variables for all the 3 blades that you see here. And in this case, we have been constraining the power, which is, we're constraining the stage power to have a feasible design. Now, in the past, Antonio already did this, and he has well documented this results, and it kind of gives like the amount of memory consumption and the number of frequencies that is required to reach, let's say, almost same level of accuracy as that of an unsteady problem. However, when we go to 3D, things become much more difficult. So over here, you see the temporal cost of running adjoint and harmonic balance, mixing plane and harmonic balance with adjoint and the direct solver. And as you can see, well, we have kind of set a limit for ourselves that we cannot go beyond 72 hours. So we cannot go beyond 3 days for one design step. And that's where you see there are like different meshes, that is M0 to M6. And at M0 is the only one that in which we can achieve a harmonic balance solution in less than 3 days. Whereas in M1, it just goes a little beyond 3 days. Also, with respect to the RAM consumption, we set ourselves a limit of 128 gigabytes. And you can see here that the harmonic balance solver, it consumes, the second mesh is almost consuming all the RAM that we had set as a limit. So it just goes to highlight that how expensive temporarily and in terms of memory a harmonic balance adjoint computation is. And this doesn't only show a problem, but it also shows us opportunity that's where we can work in the future to increase the speed of these solvers and reduce the memory consumption. Now, the final result, it looks fantastic, because over here, what you see is the 3 blades, the Stator 1, Rotor 1, and the Stator 2. And with the harmonic balance, we were able to obtain a 4.9% improvement in the performance. Whereas with the mixing plane, we had a 3.9% improvement in the performance. Now, the most visual difference between the blades is that with the rotor, in which the harmonic balance has this very typical S shape, whereas this mixing plane rotor blade has this inverted C shape. Now, we were expecting to have more answers from this simulation, but we have more questions now. So as to why these two radically different blades were obtained. Now, one of the primary reasons could be with respect to how the mesh is managed at the hub and the shroud surfaces, which has been a limitation for a long time for turbomachinery problems. Now, in future, we would like to simulate both these blades back to back in a time-accurate solver, probably within CFX, and then to have a good, valid comparison, like which design actually performs well, because harmonic balance is also a reduced order method after all. Now, about aeroelasticity. Now, aeroelasticity is another important aspect of turbo machines. So there are two very common phenomena is force response and flutter. And then we solve the equation of motion to get that. Now, this is where also I did this part of the work that I did in my PhD thesis, in which I constructed this reduced order objective function, which is based on the energy method, which gives the work done per cycle of a forcing computation, which is a blade which is isolated and is under the influence of an inlet which has a certain kind of frequencies or time varying inlet. And then we have the damping computation, in which the blades are vibrating at their pitching motion, or let's say their resonance frequency, and then that work is put into the properties, and then we multiply this with CFD with the mode that we obtain from a finite element solver. And this objective function can then be utilized for optimizing for the forced response of the turbo machine. Now, this was all in 2D, but in 3D, the problem becomes more complicated. So in this case, we have a 22 rotor blades, which is interacting with the wakes from 11 IGVs. And then if you do a Campbell diagram of this system, you can obtain the frequency crossings, which is nothing but your frequency at which you're going to have resonance. So in this case, we get the fourth mode, which has the resonance with the 11th engine order. And this is the third bending with the first torsion mode, which coincides with the 90% of the speed of rotation of this blade, which is the NASA Rotor 67. Now, based on this, I was able to simulate this vibration that was obtained from a commercial software in CFD so as to obtain the unsteady effects. And then I use this unsteady value to compute my objective function J, which I showed previously. Now, I would like to highlight a few points here. So let's say the RAM consumption for running the adjoint of this problem was close to 250 gigabytes, which is very close to the capabilities that we have at our disposal. Now, some of the key features that this particular branch of SU2, or let's say some of the features that I implemented, is the solution of flow and adjoint with deforming grid for unsteady problems, especially with harmonic fits with harmonic balance. To have imposed a user-defined mesh motion so as to define the custom vibrational motion that was obtained from commercial software, and the spectral time, the spectral grid velocity computation, which is perhaps the most computationally expensive part of the entire solver. Some quick results. So in this case, I was able to obtain a 0.2% increase in the improvement in the forced response objective, and 0.25, which was as a respect of 0.25% reduction in the aero forcing work. Now, there's a big caveat here. So these results were only for after 2 iterations of my optimization. And after that, the optimization had to be stopped. That was primarily because the mesh elements became way too coarse or way too bad for the adjoint to converge. So these are some of the problems that we see coming forward to us, and we wish to work on them in the near future. And I give the floor back to Matteo here. Thank you.
Thanks, Nitish. So I would like to close this talk by illustrating a bit what we have learned in the past 7 years. And these are not really key technical takeaways, but these are key takeaways as a scientist operating in an open source, in an open association, in an open community like SU2. So we could have been at the edge of turbomachinery of methods for simulation and design optimization of turbomachinery, because we based our developments on the ground set by this very large community, and we are very thankful for that. So it might be that you have, they said, the learning curve is steep at the beginning, but it pays off in the long run. And this is a strong message that we'd like to share with all the people that are attending the conference today. Second one, possibly not a surprise for people dealing with internal flows and statistically periodic flows like turbomachinery flows. Where turbomachinery are inherently a beast. So we have been struggling a lot with the performance, computational performance of SU2 for turbomachinery flows, but we are glad to say today that there's been a quantum leap in performance with the introduction of V7. And we are very hopeful that in the future we'll be able to improve further the performance thanks to the contribution of many of the developers that are also here today. And well, there is no free lunch, as I was saying. So becoming a SU2 developer requires effort, resilience, a lot of passion, and a fully open attitude. So there is no free lunch, but in the long run pays off, and it's really enjoyable to contribute to the advancement of knowledge in a very collaborative way. Now, for more technical tips, there are, I think, 2 well-crafted presentations by Pedro that will happen at 9:15 PDT, and I warmly invite everybody here to follow them. Now, on a more technical side, what are the challenges ahead? What we envision to be the challenges that we need still to overcome, really to be able to have a tool at our disposal that enable efficient computation and design optimization of complex turbomachinery configuration. First of all, we should invest time on making the flow solver even more robust. V7 has been a great addition, but we need to invest more time and more effort for achieving that. And first of all, we should focus on the flow solver, because the adjoint counterpart, and there will be a talk on that, the discrete adjoint counterpart will inherit. So the adjoint will intrinsically benefit from the improvement on the flow solver level, at the flow solver level. Lot of effort and lots of the focus must also be on the unsteady counterpart. So unsteady flows in turbomachines are extremely costly because you need to run many revolutions, and there is much that can be done there, and especially also related to the HP solver. It is in SU2 as of now. And when it comes to design optimization, we are still wondering whether mesh deformation is the way to go for turbomachinery design problems. Possibly not. And in case not, we would need to think of remeshing, and I think here pointwise can play a big role. Hopefully, with the contribution of many, this won't take other 7 years. Otherwise, we all become old. But before leaving you, I would like to show a sneak preview of what is upcoming. So luckily enough, we have been able to attract the interest of some Chinese colleagues, now Chinese friends, and we'll perform a blind validation of SU2 with respect to an open test case, the TU Darmstadt supersonic compressor, jointly. So Nitish and I and two colleagues in China from NPU, Northwestern Polytechnic University, and we'll present the results of this validation, blind validation study at the next GPPS conference, and then we'll release everything to the community, to the SU2 community. And with this, I would like to thank all of you for attending our talk. And of course, if you're interested to be more involved about turbo features, let us know. We are here. Thanks a lot.
Thank you very much, Matteo and Nitish, for your nice talk. We have a question from our Pedro Gomez that really deserves an answer. I'll read it. Why the heck are these features not in the develop in GitHub? Why have we not heard about them before via GitHub issues or the developer meetings? Why have you not commented when people that is me, Pedro, were working on similar methods, namely Newton-Krylov? Come on, folks. In other words, what can the foundation or the community in large do to make your life easier?
No, so well, I think his concerns are pretty genuine. But I think that we have a lot of features that right now, let's say I'm the only one here working exclusively on the code and trying to merge everything together. So it's a bit too much work on me, I would say. But let's say I'm getting there. But I'm sure pretty soon we'll have most of the features in the develop. We already have some of the major ones already in develop, which is open in a PR draft. But with respect to the Newton-Krylov, well, we have not implemented something ourselves. It's something that we have been testing from one of the previous implementations. So we are testing those methods in our test cases. So do not be, I think maybe the message went wrong that we're implementing our own. That's not true. So we are still with the foundation. Do not think otherwise, Pedro.
Yeah, thank you, Nitish. Anyway, it looks like communication as always should be improved.
Let me add one point here, Pedro. You are a PhD right now, so you know the PhD work has up and downs, and we could afford more man hours in the past because of other PhD. Now we are less people here. We are doing our best to keep up with the new developments, and the SU2-Evo project was exactly meant for that. For keeping up. So Nitish is attending the developers meeting now. We need to improve on the communication side. I'm sure that also with your help we'll do that. Thanks.
There's a question from Juan also. What is the key cause of the slow convergence of the harmonic balance approach that leads to such long computational time?
Would like to say something, or shall I?
Well, there are multiple reasons, I think. Well, first of all, like already in the steady state problem, if we have supersonic flows, it's already pretty difficult to get certain convergence. But let's say we should also be aware that this is all in V5, where we had some kind of, let's say, periodic flux losses and also some MPI errors. So I have been testing the V7. The results are much more promising, but obviously these results, what I reported there, are from V5. So I think we should also be aware of that.
And related to computational performance, Juan is also asking if you can quantify the improvement that you're seeing in V7 somehow.
So I cannot tell in numbers, really. I'll be more synthetic right now. I would say, yes, there is improvement, but yeah, by what quantity, I have to really perform neck-to-neck benchmark, but I'm still doing that.
Yeah, maybe here a couple of notes for you. On one side, the harmonic balance solver uses a fully segregated approach, meaning that we solve one time instance at a time, and then we assemble everything at the end. Definitely a performance benefit would come if we would be able to implement a fully coupled HP solver. On the other hand, regarding the improvement of performance, you could see also from the APU turbine test case. I clearly remember Salvo running this with the old version, possibly V4, in 10,000 iteration. Now it's 2,000 bit plus, bit more. So it's a substantial improvement. Then we can chat more about where we would like to go with respect to performance. So we are acquiring some astonishing results also from other solvers. And I think these other solvers should be our benchmark in the long run, the computational cost.
Okay, Matteo and Nitish, there are other questions, but we have to follow up with the next presentation. I remind all the audience that you can still send your questions by email and we make sure that they are answered.